We now know what independence means for events and for classes of events, but we'd like to understand what it means for random variables to be independent. In previous cases where we have some property of events that we'd like to extend to random variables in an appropriate fashion, for example, extending probability measure to expectation or integral, we would start with indicator functions and generalize to simple functions and generalize to measurable functions. We could view what we're about to do in that framework, but instead we're going to be a little more functorial and notice that, hey, we know what it means for sigma fields to be independent, and associated to each random variable we have a sigma field, the sigma field minimally measurable with respect to that random variable. And so that leads us to the simple definition of independence of random variables. Suppose that we have a collection of random variables, and in fact, we can be very general here and allow them to take values in any state spaces that we want. So let xi be a collection of measurable functions defined on a common probability space, taking values in some state spaces. Now, the most common example we'll be dealing with is where these are all of the form r di with respect to the Borel sigma field on those, as in random vectors taking real values in their components, and probably will largely be concerned with the case where they all take values in the same vector space Rd, or most commonly in the real line. But for much of what we're about to say, generality works just as well. Remember that sigma of xi denotes the smallest sigma subfield of f with respect to which xi is sigma of xi bi measurable. And of course we have a description of that. It's just the pullback by xi of the sigma field bi, meaning it is the set of all preimages under xi of sets bi, where bi ranges through the sigma field scripty bi. Now we define a collection of random variables like this xi to be independent if their sigma fields are independent, in the sense that we defined in the last lecture. That's what it means for random variables to be independent. Now, you might feel that the sigma fields associated to random variables are kind of nebulous objects and not fully understand what they tell us about the random variables. I know I felt that way the first 6 times that I saw this material. So let's go through carefully exactly what this says. What we're saying is that for every choice of bi's in the range sigma fields for these random variables, the events xi preimage on bi are independent. Okay? Now, what does that mean? It means that for any finite collection of them, so let's just, for the sake of notation, suppose that the set I consists of the indices from 1 up to n, we have that the probability of the intersection x1 preimage on b1, x2 preimage on b2, etc., xn preimage on bn, is equal to the product of those probabilities. Another way to write that, which is more common, is to say that the probability that x1 is in b1 and x2 is in b2 and etc. through xn is in bn is equal to the probability that x1 is in b1 times the probability that x2 is in b2 times etc. through the probability that xn is in bn. The probability that the random variables x1 through xn jointly take values in a collection b1 through bn is the product of their individual probabilities of being in those sets. We're going to explore throughout this lecture different ways of saying that same thing, but that is the definition of independence of random variables. In the last lecture, we talked about extending independence from classes to sigma fields, which worked in general provided that those classes were pi systems. Using the nice properties of preimage of measurable maps, we can extend the same idea in this context as follows. Suppose I have a collection of random variables taking values in some state spaces. And suppose that I have not the full sigma fields, but some subset of events in the range sigma fields that are pi systems. That is, each of these, a subset of that sigma field, is closed under finite intersection and generates the whole range sigma field as a sigma field. Then we can reduce our definition equivalently of independence of the random variables to saying that the preimages of the random variables on sets EI are independent when EI ranges through those subsets, script EI. We don't need to confirm it for all subsets in the BIs. This is certainly useful if we have real-valued random variables. This means we don't need to consider all possible Borel sets, which are very complicated in the range, but only restrict to any pi system that generates the full Borel sigma field. We'll look at that in a second, but let's prove this result first. So let's define Ci to be the pullback of EI by Xi. In other words, it's the set of all things of the form Xi preimage on EI, where EI ranges through the class script EI. We're going to show that those Ci's are pi systems that generate the appropriate domain sigma fields. So Ci is a pi system. Why is that? It's because of the nice properties of preimage. If I take A and B to be two sets in Ci, well, that means that they have the form Xi preimage on some set E and Xi preimage on some set F, where E and F are in script EI. And that means that the intersection of A and B is Xi preimage on E intersect Xi preimage on F, and the way preimage of any function works, that's the same thing as Xi preimage on E intersect F. Now E intersect F is back in EI because EI is a pi system. And therefore, this is the preimage of an element of EI by Xi, which is exactly to say that A intersect B is in Ci. So Ci is indeed a pi system. Now, what about the sigma field generated by Ci? So that's the sigma field generated by the pullback of script EI by Xi. But we have a nice result from an earlier lecture that you proved on your homework, that the sigma field generated by a pullback is the pullback of the generated sigma field. And by assumption, EI generates all of BI. So this is the pullback of BI, which is of course the sigma field generated by Xi. Thus, if this condition here holds, which says that all of these sets are independent, by the lemma we proved last time, if the Ci's are independent, then so are the sigma fields they generate, these guys, because the Ci's are pi systems, which tells us that these sigma fields are independent, which is exactly to say that the Xi are independent random variables. The converse is easy. If the Xi are independent, and therefore these are independent, then these subsets of those are, of course, independent as well. And so that proves this lemma. So, for example, suppose that all of our random variables are real-valued Borel random variables. We could take, for example, EI to be the set of half-infinite intervals from minus infinity up to t as t ranges through the real line. This is a pi system. The interval from minus infinity up to t intersect the interval from minus infinity up to s is the interval from minus infinity up to the minimum of s and t. And so it is again in that set, EI. So it's a pi system. We also know that it generates the Borel sigma field. I can take the difference of any two of these to get a half-open interval, and we know that the half-open intervals form a semi-algebra which generates the full Borel sigma field. And so this exactly fits the conditions of the lemma here, which means that for real-valued random variables, they are independent if and only if these sets are independent. From the definition, what that says is that we can characterize independence of real-valued random variables by this condition here. That is, the probability that x1 is less than or equal to t1 up to xn is less than or equal to tn is equal to the probability that x1 is less than or equal to t1 times up to the probability that xn is less than or equal to tn, which is, by definition, the product of the CDFs of those random variables at those different parameters t1 through tn. You might call this the joint CDF of the random variables. And so independence of real-valued random variables is equivalent to this product property. The joint CDF of the random variables is the product of the CDFs of the random variables. This product structure is very general, and in fact it has to do with the characterization in terms of the joint law of the random variables being product measure. We've talked about joint laws of real-valued random variables, but the same idea applies to general random variables like we're dealing with now. Suppose I have a collection of random variables that have values in different state spaces. I can put them together in a kind of vector and talk about the joint law of that. The joint law of that collection of random variables is going to be the probability measure on the product sigma field that is defined by the probability measure in the domain pushed forward by this map x to the product space. So just to be clear, remember that the product sigma field is the sigma field generated by all Cartesian products of sets in the individual sigma fields. And it is a sigma field over the product S1 times Sn, which is the range of this function. Now, in the case we're usually most interested in, if all of the state spaces are just the real line equipped with the Borel sigma field, then, as we noted, the product sigma field is the Borel sigma field over Rn. And so this corresponds with our earlier notion of joint law of random variables. One way or another, what we're saying is that the joint law of x is the probability measure on the product space defined by the measure of a product set B under mu x is equal to the probability that x is in that set B. The theorem, which characterizes independence now, is that in this general context, a finite collection of random variables x1 through xn are independent if and only if their joint law is the product measure of their individual laws. This follows very quickly from the definition. Let's take any collection of events bi in the range sigma field scripty bi and look at the probability that x1 is in b1, x2 is in b2, up to xn is in bn. Well, that's the same thing as asking for this vector of those random variables to be in the product of b1 through bn, which is by definition the law of x at the event b1 times bn. Thus, if the joint law is the product measure, then by the rectangular property of product measure, this will equal mu of x1 of b1 times mu of xn of bn, which by definition is the probability that x1 is in b1 up to the probability that xn is in bn. And so that tells us that x1 through xn are independent. So that gives us the reverse direction here. For the forward direction, if we know that x1 through xn are independent, then look at the probability that that vector of x's is in the product space. So that is, reading upward on the right, just the probability that x1 is in b1 and x2 is in b2 and xn is in bn. And because of the independence, that factors as the product that x1 is in b1 up to the probability that xn is in bn. Well, that's the individual law mu x1 of b1 times up to the individual law mu xn of bn, which for product sets like b1 times up to bn is the product measure on that product set. And so we've verified that the joint law on product sets coincides with the product measure. But we know that that uniquely characterizes the product measure. Alternatively, we can think of the fact that the set of Cartesian products like this is a pi system which generates the whole product measure by definition. And when two measures agree on a pi system that generates the whole sigma field, they agree everywhere. So one way or another, that gives us the proof in the other direction. Independence of random variables is equivalent to their joint law being the product of their individual laws. One quick consequence of that is that we can now relate this notion of independence of random variables to an earlier independence type notion that we developed a few lectures ago, uncorrelated random variables. Suppose I have two random variables x and y, both real valued, defined on the same probability space, and both L2, square integrable. If they happen to be independent, then they are uncorrelated. Their covariance is 0. Well, that's just a calculation now. The covariance is defined to be the expected value of the product minus the product of the expected values. But we can compute those expected values in terms of the joint laws of these random variables by the change of variables theorem. The change of variables theorem will tell us that the expected value of the function xy is the integral of little xy integrated against the joint law of x and y. Now, if those are independent, then this is the integral of xy against the product measure, mu x dx, mu y dy, and by Fubini's theorem, which applies because x is in L2 and therefore in L1 of this probability measure, and y is in L2, therefore L1 of that probability measure, this can be evaluated as an iterated integral. But of course, with respect to the inside integral for dx, y is a constant, so we can move it outside. In other words, we're noticing that this function xy is a tensor product function. And so this just becomes the integral of y mu y of dy times the integral of x mu x of dx. But those, again using the change of variables formula, are the expected value of y times the expected value of x. And so that says that this is 0. Independent random variables that are L2 are uncorrelated. The converse, however, is typically false. Being uncorrelated is strictly weaker than being independent. And we'll see examples of that at the end of this lecture. Now here we saw a factorization property of expectations. In the case where the random variables were L2, we saw that the expected value of xy, for x and y independent, factored as the expected value of x times the expected value of y. Well, actually this didn't require L2, it only required L1. And it works more generally. So here's the proposition. Suppose I have a collection of independent random variables, x1 through xn, that are in L1. Then their product is also in L1, and the expected value of the product is the product of the expected values. Notice that in general, L1 is not closed under product. The product of a bunch of L1 random variables is typically not L1. Usually you have to downgrade integrability. We know that the product of two L2 functions is in L1. That's because of the Cauchy-Schwarz inequality. Here, this independence of the random variables allows us to take products of L1 random variables and stay in L1 because of this factorization property. So this is again just a calculation. Let's do it. So let's put together our random variables into a random vector x. And by their independence, we know that the joint law of x is the product measure of the individual xi's. Now we'll use the change of variables theorem and Tonelli's theorem, like we did last time, except using Fubini there because we didn't know that they were positive, to write this expected value of the product as the integral over the product space of little x1 product up to little xn against the joint law. That's going to be over Rn, where this vector x lives. Because they're independent, this is the product measure, and therefore we'll use Tonelli's theorem to evaluate this as an iterated integral. And the function that we're integrating is a tensor product function again, and so we can factor out each of the pieces into the only one integral where it occurs, and this iterated integral becomes just a product of one-dimensional integrals, which, again by the change of variables formula, is the product of the absolute expected values, which are the L1 norms of these L1 functions, and so that's finite. So that tells us that this product, x1 through xn, is in L1. Now we need to see that this factorization property holds, and to do that we just repeat the exact same calculation using Fubini instead of Tonelli, because we're not going to have the absolute values anymore. So random variables have expectations of products that factor. In fact, we'll see shortly that independence can be thought of exactly as such an expectation factorization property. Here is a very general theorem in that direction. Suppose we have a collection of random variables, again, even in this very general setting where they take values in different state spaces. We'll put them together into a vector x, like we have been. Then the following conditions are equivalent. Those random variables are independent, or their joint law is the product measure of their individual laws. We already saw that implication. Or we have this kind of expectation factorization property. For any bounded measurable functions in the range, the expected value of those functions of the random variables is the product of the expected values of those functions. Now, in the previous example, where we had real-valued random variables that were assumed to be L1, we took those functions to be absolute value, or just the identity function. If we don't know that our functions are L1, we can't necessarily even compute these expected values, even for real-valued ones, unless we have a condition on the f that makes them L1. And that's what this does. If I have any bounded function of a random variable, it will be an L1 random variable. So those three conditions are always equivalent. And now if we have a little bit of topological structure on the state space, namely if we assume, as will usually be the case in this course, that the state space consists of a Euclidean space equipped with the Borel sigma field, then we can also include these two conditions in the full list of equivalent conditions. Instead of insisting that those test functions f1 through fn be bounded, or be just bounded, we can make even stronger restrictions. We can restrict them to be continuous and compactly supported. Those are bounded measurable functions, but it's a much smaller class. We could also restrict those functions, instead of just being any bounded functions, to be this very, very small class of functions here, consisting of indicator functions of products of half-infinite intervals, corresponding exactly to the condition that we already proved of independence being characterized in terms of the joint CDF factoring as a product of CDFs. We've actually already largely proved this theorem. So the equivalence of 1 and 2 was 2 slides ago. The fact that 2 implies 3 in the general case, and 4 and 5 in the special case of having the topology to define what these things mean, follows exactly like the proof on the previous slide by doing the change of variables formula on both sides, and then using Fubini's theorem to factor the integral as a product, as it will be, because the joint law is a product measure. Now, these conditions 4 and 5, which have smaller classes of test functions than the bounded measurable functions, those actually each imply the more general one in the Euclidean setting where they make sense by the Dynkin multiplicative systems theorem. It's easy to verify that each of these forms a multiplicative system. In each case, we'll define a subspace of the bounded measurable functions to be the set of bounded measurable functions for which this condition holds. And we'll, as should now be standard to you from all the applications we've seen, show that that subspace is one for which the Dynkin theorem applies. we need to verify that it's closed under bounded convergence. And we'll do that by repeated application of the monotone or the dominated convergence theorem. And so therefore, Dynkin's theorem will allow us to generalize this holding for these classes of functions, which are subsets of the ones that we stated by assumption, to the full space of bounded functions measurable with respect to the sigma field generated by these functions. And it's a standard exercise to show that in both of those cases, the sigma field generated is the full Borel sigma field. So that shows us that 4 and 5 imply 3. And so to complete the equivalence of all of these conditions, it suffices to show that 3 implies 1. But for that, we just say, hey, if 3 holds for all bounded measurable functions, it certainly holds for functions of the form fi equal to the indicator of bi, where bi is any chosen measurable set in the sigma field, scripty bi. Now, the expected value of fi of xi, which is the expected value of the indicator bi of xi, by the change of variables theorem, is the integral of that indicator d mu xi, which is the integral over bi of d mu xi, which is exactly the probability that xi is in bi. And, of course, following the same calculation but with a product of these inside, and noting the fact that the product is equal to the integral of the indicator of b1 at little x1 times the indicator of bn at little xn against the joint law. But this is a tensor product of indicator functions, and as we've shown, that's the indicator function of the product. And so that exactly evaluates to the probability that x vector is in b1 times bn. And so we see that this equation holding for those functions exactly says that this probability is equal to the product of those probabilities, which is to say that x1 through xn are indeed independent. And so this theorem is proved. Now, let's talk about groupings of independent random variables and how that affects their independence. To do that, we need to talk about groupings of independent events. So here is a little lemma. Suppose that I have a collection of sigma fields over a fixed domain, and suppose that I partition them. I take the first 3 sigma fields, and then the next 2, and then the next 1, and then the next 7, and so forth. And I'd like to consider those as groupings. So what I'll do is I'll take the sigma field generated by the first 3 and call that a new sigma field, and then the sigma field generated by the next 2 and call that its own sigma field, and so on down the line. Well, if the original sigma fields, f1 through fn, are all independent from each other, then these grouped sigma fields are also independent from each other. That's what we'd like to prove here. And honestly, the only hard part about this proof is the awful notation of all of the groupings. And so just to make things easier, I'm going to do it in a special case, but you'll see how the proof works in general. Let's just take a grouping of 2. G1 is the sigma field generated by f1 through fm, and G2 is the sigma field generated by fm plus 1 through fn. Well, we know that sigma fields of independent pi systems are independent. So what we'd like to do is say, hey, this is a pi system and this is a pi system, and therefore their sigma fields are independent because these ones are independent from each other. But that's not true. These are not pi systems. The union of 2 sigma fields is not a pi system. It's not necessarily closed under intersection. But that's okay. All we need to do is turn them into pi systems that still generate the same overall sigma fields G1 and G2. And to do that, well, a pi system is something that's closed under finite intersection, so we just close it under finite intersection. We'll let C1 be the set of all intersections of the form A1 intersect up to AM, where each AI is taken from one of the appropriate FIs between 1 and M. And similarly, C2 will be the set of all things of the form am plus 1 intersected up to an, where each ai is taken from the appropriate sigma fields. Those are pi systems by construction. They are evidently closed under finite intersection. They are also independent. Why is that? Well, let's take a C1 in scripty C1 and a C2 in scripty C2. Well, that means that we can write C1 as the intersection A1 up to AM, and we can write C2 as the intersection AM plus 1 up to AN. And therefore, if I want to calculate the probability of C1 intersect C2, that's just the probability of the intersection all the way. Now, those AMs are all taken from these independent sigma fields. And so this whole thing factors as the probability of A1 times the probability of A2 times probability of AM times the probability of AM plus 1 times the probability of AN. But now I can regroup those in the appropriate groupings and say, hey, also F1 up to Fm alone are independent. And so that product of probabilities there is also just the probability of A1 intersected up to AM. And Fm plus 1 through Fn are all independent, and so the events Am plus 1 through An are all independent on their own. And so that product also can be regrouped as the probability of Am plus 1 intersected up to An. And there you have it. That shows us that for any two events C1 and C2 in the classes scripty C1 and scripty C2, the product of their intersection is the product of their probabilities. And so that shows that these pi systems are independent. Great. So now I have a lemma from last lecture which tells us that the sigma fields that they generate are independent. But the sigma field generated by C1 is actually all of G1. Why is that? Because, look, if I take any Fi and I take any event in it, Ai, I could write that as the intersection of the whole sample space with itself with Ai. And that, by definition, is in C1 or C2 if you're taking the AI in the appropriate place later. So C1 contains the union, F1 up to Fm. And C2 contains the union, Fm plus 1 up to Fn. And therefore, the sigma field that it generates contains the sigma field generated by F1 through Fm, which is G1. And similarly, this contains that, but of course is equal to it since the other containment is clear. And so that shows that these two are independent. The exact same proof works in general for larger numbers. It's just a matter of keeping track of all of those indices. Now, a nice corollary of that is that we can group independent random variables. Again, even in this wide general context of having random variables with different state spaces. Suppose that I have a finite collection of independent random variables. Let's say they're indexed by the integers from 1 up to n, and suppose that I have an integer partition of those indices. And suppose that I take any functions of those partitioned collections of spaces. Then the compositions of those functions with the partitioned random variables are still independent. Notationally, that looks like a mess, but this example should make clear exactly what's going on here. In other words, what we're saying is, if I have random variables, say x1 through x5, that are all independent, then so are the classes x1 and x2, x3 and x4, and x5. Those classes of random variables are independent, and in particular, what that means is that if I take these three random variables, some function of x1 and x2, some function of x3 and x4, and some function of x5, then those will also be independent. Why is that? Well, let's do it again in the special case that we had last time. So let's look at partitioning of x1 through xm versus xm plus 1 through xn. Let's let y1 be some function f1 of x1 through xm, and y2 be some function of xm plus 1 through xn. Well, the sigma field generated by y1 is then certainly contained in the sigma field generated by x1 through xm. That is the easy direction of the Doob-Dinkin decomposition theorem. And similarly, the sigma field generated by y2 is contained in the sigma field generated by xm plus 1 up to xn. To be clear, all of this is assuming that the functions involved are measurable functions in the appropriate sense. Measurable with respect to the range sigma field being the Borel sigma field. Well, this is the sigma field generated by the union of the sigma fields generated by each of the x1 through xm. And this is the sigma field generated by the union of the sigma fields xm plus 1 through sigma of xn. And so by the previous lemma, these are independent sigma fields as well. And that means that y1 and y2 are independent. So independence of sigma fields and of random variables is very nice with respect to groupings, as you would hope. Now let's come back to that question from earlier in the lecture about independence versus correlation. Here is an example, which we can now show using the tools we have, of a pair of random variables that are uncorrelated but not independent. And in fact, that's the general situation. It's rare for uncorrelated random variables to be truly independent. Let's take our random variables x and y to have the form x and x times z, where z is a random variable that is independent from x. Now, if I had something like x and y times z here, where x, y, and z were all independent, then the previous lemma would tell us that x and yz are independent. But that's not the situation we're in. X is certainly not independent from x in general. In fact, you can check that it's only independent from itself if it's a constant. In fact, we'll see in a few minutes that generally speaking, these two are not independent from each other. However, if z has expectation 0, then these two will be uncorrelated. That is, provided correlation even makes sense. We need both of the random variables x and y to be L2. So let's assume that x is in L2, and to make things easy, let's assume that z is a bounded random variable, because then z times x is certainly also in L2. Now let's calculate the covariance of x and y in this setting. So that's by definition the expected value of the product minus the product of the expected values. Well, the expected value of xy is the expected value of x squared z. The expected value of y is the expected value of xz. Now x and z are assumed to be independent. We also know that x squared and z are independent from the previous lemma. And since x is in L2, x squared is in L1. So everything squares out, and we can factorize this as the expected value of x squared times the expected value of z minus the expected value of x times the expected value of x times the expected value of z. And hey, our assumption here was that the expected value of z is 0, which means that this is 0. So those are indeed uncorrelated random variables. But are they independent? Well, let's take this a little bit further. Let's try to calculate the expected value of x to the n, y to the m for some powers n and m. Well, we don't know that we can actually define that. X to the n times y to the m may not be an L1 random variable. So we'll make some assumptions that will allow all the calculations to be justified here in a second. But let's just do this the way we know it will have to work if everything is well defined. This is just the expected value of x to the n times x to the m, z to the m, which we can recombine as the expected value of x to the n plus m, z to the m. And now, if x to the n plus m happens to be in L1, and z to the m is in L1 because it's bounded, then we know that this will factor as the expected value of x to the n plus m times the expected value of z to the m. Now on the other hand, if I take the expected value of x to the n times the expected value of y to the m, doing the same calculation, what we'll find is that that's equal to the expected value of x to the n times the expected value of x to the m times the expected value of z to the m. Again, that will be valid provided that both x to the n and x to the m are in L1. But as you can guess, these two things are typically not going to be equal. Now we got that they were equal in the special case up above where n and m are both 1 because of the assumption that z had expected value 0. So, if that term happens to be 0, then sure, these are going to be equal. But they're not really structurally equal because of this factorization property. Expected value of x to the n plus m typically will not equal expected value of x to the n times expected value of x to the m. That sort of looks like x being independent from itself, which, as we've noted, really only holds when x is a constant. In fact, we can show that this doesn't work in lots of situations. We just need to make sure these conditions are met, and we can do that by, for example, taking x to be a standard normal random variable. Standard normal random variables have finite moments of all orders, as we've previously calculated. And as for z, well, we have lots of choices, but we could, for example, take z to be a Rademacher random variable, which is a symmetric version of a Bernoulli. That is, its law could be 1/2 a point mass at 1 plus 1/2 a point mass at -1. Then it does have expectation 0, and it is bounded by 1. Now let's just check to see what happens with these equations here. Let's do it with n and m both 2. Then the expected value of x to the 2 plus 2 is the fourth moment of a Gaussian, and we've seen what that is before. It's equal to 4 minus 1 double factorial, or 3 times 1, which is 3. On the other hand, if I take the expected value of x squared times itself, for a standard normal, that's just 1. And so, indeed, these two do not agree. But with m equal to 2 here, the expected value of z squared here is just 1, as you can check. And so this is an example. With x being a standard normal and z being a Rademacher, x and xz are not independent, even though they are uncorrelated. Let's emphasize this point one more time. How did this show that these two are not independent? Well, we have a theorem which tells us one of many equivalent formulations of independence. But one of those characterizations was factorization of expected values when the functions involved are appropriately integrable. If x and y are independent, then x to the n and y to the m are independent by the previous slide. And if x to the n and y to the m are both L1, then those random variables being independent implies that the expected value of their product is the product of their expected values. That failure here shows that these two are not independent. Now, if we're working with random variables for which x to the n is integrable for all n, then this gives us a powerful connection between probability theory and combinatorics through what's called the method of moments. And here let me display our first result, or invitation to the method of moments, as follows. Suppose that I have a collection of random variables, now real-valued random variables. And for simplicity, let's make sure they're all bounded random variables. Okay, again, that just means that there's some constant so that their absolute values are all less than or equal to that constant with probability 1. That's a convenient assumption because if you have a bounded random variable, then any of its powers will be also bounded. And since bounded random variables are in L1, that means that all powers of these bounded random variables are integrable, which means that the expectation factorization property of L1 random variables holds for all of those. And in particular, it means that if I have independent bounded random variables, then the expected value of a product of their powers factors as the product of the expected values of their powers. That just follows exactly by what we said on the last slide. x1 to the k1 through xn to the kn are independent because x1 through xn are independent, and the power functions are measurable functions. And they are in L1 by what we set up here, and therefore this follows by a theorem we proved earlier this lecture. The very useful fact is that actually you can go backwards, in this case of bounded random variables. Suppose that I have a collection of random variables and I know that they have this moment factorization property. Their joint moments factor as individual moments. Then you can conclude that those random variables are in fact independent. And that is going to be on your homework. So now we've learned a lot about independence of random variables. The next topic we're going to move into is understanding infinite sequences of independent random variables. But first, we need to see that such sequences exist.